So they're your choices, and I don't really want to adjust it too much because it would just be a redesign. We will make any changes we need to though. So for those of you who've been in 225 or otherwise are interested, you'll know that we've got a differential amplifier with some degeneration, which is a local feedback, R1 and R2, and we've got a current mirror and some other transistors. This one behaves as a diode and this one is a helper of some kind, whose job is to balance the two currents in the collectors of Q6 and Q5. And we've got some fancy looking current source with an awful lot of diodes. This is our feedback network, and we've got our emitter follower with a common emitter amplifier and some global loop compensation here. The job of C1 is to make sure that the poles of the open loop system are set in such a way that when we close the feedback loop it doesn't oscillate. That's the middle part of 225, taught by me. And we've got some biasing network, a fairly simple one here, which aims to spread the bases of Q12 and Q13 in such a way that there's a quiescent current. And we've got a simpler current source here. And we've got two output resistors, maybe you wouldn't call them output resistors, I call them sort of emitter resistors because they're in the emitter of Q12 and Q13. And their job is to provide some electrical feedback and prevent thermal runaway in the output stage. Help prevent thermal runaway in the output stage. So we'll start with this current source. Now, when you're simulating things and you just want a voltage drop, you might be tempted to do this sort of thing. 0.7 volts per diode. You can work out the drop if you want. You wouldn't do it in practice. It takes up a lot of room on a circuit board, and the components cost money, and the more components you put in, the more likely the circuit is to fail in a certain amount of time. Mean time before failure goes down, just because the chances of any one of them going adds to the likelihood of failure. There's a lot of different ways we can do it, but if you're in a rush and you're in the simulator, sometimes you might be tempted to do that sort of thing, but there are other ways. So we'll press F5 to delete things, and we'll just delete this lot. Get rid of that. Oop, not that. F9 was undo. And we might press F8 and move this wire up, and maybe F3, and then add this bit of wire back in. Pull that up there like that. Maybe move this down a bit. Add a bit there. Might even move these up somewhat. Move this over. There we go. That's not too bad. So we need to do some biasing in this space that used to contain diodes, but before we get to that, I think we ought to do a little bit more with the transistors themselves. This, I right click just then. This one is a PNP, and that's all it tells us. And actually, SPICE has a model for a PNP transistor and an NPN transistor, which is incredibly simple. And it's most like the sort of transistor you might find on an IC. Even then, it's a pretty poor guess. If you use this model, you won't get very realistic simulations, and things that work in the simulator won't work in real life, and things that work in real life the simulator will tell you they don't work. So we need to be careful, and we need to pick models which have realistic parameters, because your job of your circuit simulator is to try to model things that you're going to build in practice, and if your models don't agree with the transistors you've got in the drawers in your lab, you've got a big problem. So we must try and choose a better transistor. So I right click, pick a new transistor. Now, we want to be a small signal transistor, and we don't want to have any chance of it blowing up. So we've got 15 volts on this supply, 15 volts on this supply, so the most we can have is 40, there's 30 across the lot. So we could conceivably choose the 2 and 3906 if we wanted to. Usually in these sort of things I'll pick something that's a little different from that. My favourite is the ZTX 753. Tend to use a lot of them. They make quite good switches as well, and it's nice for me to be able to use one transistor for more or less everything. some more or less all sort of small signal and switching up to a couple of watts type thing. Some people say, oh, it's a switching transistor, you mustn't, how dare you. Okay, come and get me then. So, you know, when a transistor is made, somebody doesn't sit down with it in the factory and go, now look, you're a switching transistor, and if anybody tries to put you in an amplifier, you just sit there and you don't work. Of course it will work. Anybody says otherwise is mad. Right, I'm going to put a Zener diode in to bias the lower transistor in this cascode current source. And well, I don't want to use the 1N750 because I don't like the model for it. So we'll put in this BZX84 series, and it's 6V2, 6.2 volt breakdown. So I should expect this node here, the base of Q7, to lay 6.2 volts below the base of Q8 if I biased everything properly. We need to pick a model for the diodes as well, and the standard one is 1M4148. You'll find these components in the stores in the EEE department as well, so that's handy. And the way the source should work, top bit, we've got diode and diodes 1.4 volts to there, we've got 0.7 there, so we're left with 0.7 across R3. So we ought to find I is V upon R, so 0.7 over 100, so we'll end up with about 7 milliamps or so flowing through R3 and into the emitter of Q8. A small fraction of that current will flow out of the base, but the very great majority of it will flow into the collector, because the alpha, which is the column-based current gain, is very close to unity. So most of it will flow out of the collector. And it will flow, that's enough to make a current source on its own. You don't really need Q7 and D3 and all the, well, you need R4 to take the current from these two. But we can make this Cascode current source, which has several advantages. Now, whether those advantages are sensible in this location or not is another matter, but this is what was here when we started, so this is what we'll do this as well as we can. And if we decide we want to throw it away and use something else, we could. The reason you might want to deal with this Cascode current source instead of just a regular current source like we've got over here is you don't want the current to change at all. You want it to be constant, which is why I've got a constant current source. But there's a couple of methods by which the current can be influenced by what happens effectively on the output node. As far as this current source is concerned, this is the output node. It's the current flows out of Q7's collector and into the rest of the circuit, which in this case is a current mirrored differential stage. So what could go wrong? Well, this junction here should be reverse biased, and so should this one, which is why I've put this thing to spread the voltages between these two nodes. There's a depletion capacitance, reverse depletion capacitance in this junction and in this one. This is the one that I'm interested in a minute. If I had a little signal injected here, there will be, so there's some voltage swing, a dV by dt. If there's a dV by dt here, and there's a capacitance in here, let me just put the capacitor in for the sake of argument. I don't have to, it's in the model already. Inside the model of the transistor, the equations account for it, but that's where it would be. This I will call it CCB, my reverse bias collector-based depletion capacitance. If I've got a dV by dt here, I should have a current in this capacitor because it will charge and discharge according to the change of voltage on the emitter. Emitters of Q5 and Q6. Ignoring R1 and R2 for a bit. If that happens, there'll be a current flowing in C3, and that current has to go somewhere. Now, some of it will go through R4, some of it will go through D3. It's a signal current, remember, so it's quite happy to go upwards through these components, even though the DC might make you think it should go down towards the ground. Actually, the signal is quite happy to go down here and up here, and then along the rail into the ground that way. Signals always want to get to ground. So it might also go into the base of this transistor, which would be very sad, because if it did, it would change the base current. And of course the base current and the collector current are related by the beta. And this is bad news. Or you can think about it as the current that flows in here will change the VBE, and the collector current and VBE are related by the GM. Your choice how you think about it. But in any case, any change in current on the base will arrange a change in current in the collector, and this is terrible because we want a constant current source. So we don't want to have this happening. So we've got to be careful about any swing here. Another problem is there is actually a little resistor in here as well. And if you remember back to 118, there was an output characteristic of a transistor, and it looks a bit like this. This is my graph. Ah, it's disappeared. Alright, there's my axes. I think we found the limitations of P-Spice at drawing, of LT-Spice at drawing graphs. And this is one output characteristic line. And this is another output characteristic line. I'll do one more. This is another output characteristic line. A bit ridiculous in shape, but whatever. So this is VCE, this is IC, and these are the output lines that you get with VBE increasing in that direction or IB increasing in that direction. This is the forward active region. This is the region where it acts as a switch. And we want to keep in this region here. Now, if I start swinging big dV by dt on this node, what I have is I'm moving up and down this line, because this line is VCE, and VCE is that voltage between the collector and the emitter. As I move, presuming this is constant and this is changing, VCE must change, I move back and forth across this line, even for a fixed VBE, whatever this VBE is, doesn't really matter. I will move up and down this line, I'll get a slight change in IC. And this is bad news, because I want this constant current source to give me a constant IC no matter what. So in practice, what I'd like to have from my transistor, if I could, is something that's a bit more like that, where this line moves to here. Then it doesn't matter what happens to VCE, the current doesn't change, and that's the ideal situation. Now, when we're modelling a transistor, we usually would have a hybrid pi model, and I'll draw it up here just for the sake of argument. You don't have to draw the pi model in Spice. Pi will do it all for you. You just put the transistors down and it does the necessary calculations, depending on what sort of modelling you're asking it to do. If you're asking it to make an AC simulation, we will discuss a simulation later as well. If you ask it to an AC simulation, it effectively does this, but it does it as a matrix for all the components and solves them for you without too much trouble usually, if you design your circuit well. Now, if I had just this current source, this is base emitter collector. It's my RBE, this is my GMVB or my beta IB. My IB is the current that flows there, and the VB is the voltage across RBE, which is R11 in this case. So, if there's nothing else between the collector and the emitter, the current that flows must only be due to the current source. And in that case, whatever current is demanded is what will flow, and any change in VCE doesn't really make any difference, and we'll get the situation where we've got the flat line on the output characteristic. The problem is you can't actually make a transistor with a dead flat line on the output characteristic in the forward active region. They all have a little bit of a slope. Now the slope I've drawn in the diagram is perhaps a little exaggerated, but it's there, and if you want to make a really good current source, you need to think a bit about it. The way we will usually model it in the hybrid pi is to add a resistance in here, and that resistance is well, this is di and this is dV, and the units of ohms are as V over I, so di by dV, so this will be to do with the resistance, in fact 1 over the resistance probably. So we'll call this RCE. It's effectively a resistance that models this slopiness. And of course the slopier it is, the smaller that resistance will be. So this RCE is smaller up here than it is down here, and RCE here is infinite, which is cracking, except we can't actually get that in practice. So we want to be a bit careful about swinging a voltage on this node. Firstly, because we'll get capacitive coupling through the depletion capacitance in the collector base junction. Secondly, as we adjust VCE, we will effectively adjust the size of the base region, and that changes the likelihood of a carrier recombining as it passes from the emitter to the collector, because it has less far to go as a minority carrier in the base. Of course, it doesn't have quite so far to go, it's got a better chance of getting to the collector. So we want to try to ameliorate the effects of any change here, adjusting VCE. So we can do that. We can get rid of both of these problems to a large extent. And the way we do is with this Cascone source. What we actually have here is effectively a common base setup followed by a common base setup, which is not quite what you would call Cascone, but I will call it Cascone current source. One thing we need to do is decouple these nodes. If we don't do that, it won't go well for us. Oh, I put it in the wrong place. I can decouple them to the high rail. The reasons for that we can come back to in a bit. Make them nice and big. I don't know the exact values, but I'll probably use whatever I've got in the drawer that's plausible. If I'm actually building it in practice, there'll be another one here as well, and another one here that I shan't bother to draw, maybe 220 now. And the C3 will be electrolytic, and the C5 will be some sort of plastic, either polyester or polypropylene, or one of those. Might even be ceramic, and we will discuss the capacitor in a bit. But we must make sure that both of the bases look like they're grounded, and they're grounded by virtue of a signal here flows through that capacitor, into the rail, into the ground, through the supply. You could put them to ground here as well, next to the 1000 ohms if you wanted to. I will not do that. It's not tradition or anything. All it comes down to is if this voltage is considerably higher than 1.4 plus 6.2, you'll need a bigger working voltage on this cap, and that'll probably make it more expensive or physically larger if you put it down here than up here. So usually we put them up there. Back to the how does this transistor help? Well, I've got my 0.7 across here and I've 0.7 there and 0.7 there, so I've got one lot of 0.7 across R3. So the current in R3 will be V upon, I will be V upon I will be V upon R. The current will be V upon R, so 0.7 across 100 ohms should be about 7 milliamps. In fact, it will probably be about 6.5. I should have thought. Depends a bit on what we set R4 as. So current flows into the emitter. A little bit comes out of the base, and because it's DC, it will flow through the Zener diode and through R4 into the ground. And that will be the base current that's required to support that collector current and emitter current. And the rest of the emitter current will go into the collector. Most importantly, this node is fixed in voltage. It's fixed in voltage by virtue of 15 less one lot of 0.7 less another lot of 0.7 less one lot of 6.2 add one lot of 0.7. Then this node is fixed. Because it's fixed, the VCE of this device is not changing. Consequently, the current that flows out of this collector should be constant. It should not be subject to the slopiness of the line. Even though the line for this transistor does slope, because we're not actually changing this VCE at all, it should be fixed. Moreover, there should be no signals on this node, because the signals which exist down here should be shielded from this node by this transistor we've added. So if this node is not changing in voltage, no dV by dt on it, doesn't matter that there's a capacitor here inside Q8's collector base depletion, because if there's no dV by dt here and this node is decoupled to ground, there's no dV by dt here, even though there is a capacitor, there shan't be any current flowing through it because the voltage across its terminals isn't changing. So there can't be any signal injection into the base from here. This is great because we don't want to modulate the base, we want to have nice fixed voltage to give us nice fixed current. So as far as Q8 is concerned, the two things about the transistor that I discuss on the graph, and also the discussion of the capacitance down here. From this transistor's point of view, they don't exist. They don't exist because we've shielded this transistor from any dV by dt down here by Q7. The job of Q7 is simply to pass the collector current of Q8 to the collector current of Q8 into the emitter of Q7 and then out of the collector of Q7 onto this rail. It doesn't really matter if we adjust this voltage. There will be some injection of signal, but it should be decoupled to the rail. If this one changes up and down, yes, there will be a change in the VC of Q7, but it will not be anything like as bad as if we only had Q8 without Q7 there to help it out. So reasons for doing this are to do with making a more constant current source, which is no surprise. And the cost is, we added a transistor, we had D3 and we had C4, and C5 in practice will also have an equivalent here. But in the SPICE, C3 is perfect. We don't have to worry about adding C5, but we will talk about why we need it in practice in a bit. We've still got to have R4 either way. The value of R4 I haven't checked, but we could simulate just this bit now, leaving out the rest, and see what happens. We won't though, we'll move on. With respect to why C3 needs C5 to help it out, when they're making the electrolytic capacitors, what they do in the simplest terms is you get a bit of aluminium foil, like kitchen foil, and you spread something on it that looks very much like peanut butter, smooth peanut butter, not with the crunchy lumps, and you put another bit of aluminium foil on top and you sort of roll it up like you'd roll a bit of paper around a pencil, and you put a couple of electrodes in, and it's one electrode on one spiral and one electrode on the other spiral, and that's your capacitor. It's not really peanut butter. It really is aluminium foil though, more or less. And this is bad news, because when you wind wires or conductors around things, even winding a bit of wire around a loo roll, you'll make a inductor. And what we really want here is capacitance. We want the impedance of this component to drop as frequency goes up. But in fact what we have is a capacitor, which is ideal, and then we have some effective series resistance, which is a dissipative element. So when we have a big di by dt in a capacitor over and over and over, the capacitor starts to get hot. It does this because it's aligning, well, we best not get into it because I'm at risk of saying something that isn't technically correct. We are polarizing the material. Not just polarizing it in a DC sense, but we are, every time we put a signal in, we are changing the amount of polarization, and that requires us to do a certain amount of work. And the result of that work being done is that heat is generated. So the real capacitor will get hot, and we call it effective series resistance. There is also the resistance, physical resistance of the metallic components, the aluminium foils and the legs as well. What is more, there is the inductance of the legs and of the aluminium spirals that are making up the device, and also there is a dissipative element where if you were to charge up capacitor and leave it on a desk with its terminals just open circuit and leave it for a long time, eventually it will discharge itself. So we've got a parasitic parallel resistance and a capacitor discharge with the current like that. So this is our capacitor, and these are our capacitor terminals. This is the ideal capacitor. These are all the little problems with it. This is bad because if we stuff this lot in this space and said I want a signal to go up through here, and it's high frequency signal, well yes, through the capacitor fine, through the resistor if it's nice and small, get to the inductor, oh dear, J omega L, omega's getting bigger, impedance is going up, chances of the signal passing going down. So we've got to be a bit careful. the polyester or the polypropylene, any of the plastic capacitors or the ceramic capacitors aren't made with this spiral winding inside. They're made by a different method. Often they're interdigitated, which means it's like putting your fingers together, sort of, to make sandwiches with your fingers being all the slices of bread. And that's how they get the bigger surface area. You can't make as bigger capacitance for a given physical size, but you don't get the parasitic inductance problems nearly as badly. So oftentimes you'll have an electrolytic to deal with the low frequencies with a nice big capacity, but in a fairly small volume. And you'll have the polyester, polypropylene, whatever it happens to be, polystyrene, to deal with the higher frequencies where it doesn't have such a bad parasitic inductance. So in practice you will need them both, and sometimes even there is a third, 100 picofarads or so. But in SPICE, unless we explain to SPICE that there's something wrong with C3, it's going to think it's perfect and it's great at all frequencies, no inductance, nothing like that. So I don't actually need to put this in the simulation, it won't do anything. But when I actually build the circuit, I've got to remember to put it in. You must decouple your nodes properly. You might even consider decoupling this node. I won't. I can't see any reason not to, but just in case. So that's the current source, and if I was to take it and simulate it, I don't know if I could just steal it away and have a go. Tell you what, instead of stealing it away, what I'll do is I'll cut that, ground that. We'll switch that off for a bit, and we'll put a load resistor in here. Oh, actually, I tell you what, rather than load resistor, if we want to be proper, we'll put a voltage source. The voltage source in this case is just a thing that allows me to measure current. I could also, if I wanted to, investigate the effects of changing the size of this voltage source. Let's call it 5 volts. Nah, 2 volts. Because this will be about 2 volts, this node here. So if I was to run this now, don't know if it'll run, but we shall see. We'll simulate, edit the simulation command. I want the operating point, DC conditions, which is .op. And we'll have a go to see if I get this. Not very helpful to get this box. If I run my mouse over certain parts of the circuit, in the status bar on the left hand side, which is just down here, I should get information. So the current in the resistor, 7.3 milliamps. I think I said it'd be a bit less than 7, so apparently I got that wrong. And the current in this diode, 7 milliamps, 7 milliamps, 7 milliamps. It says minus, but that's only because it's thinking about the anode current, and the anode current's actually flowing out of the anode. 7 milliamps. Base current, 34 micro, emitter current 7.3, basically 7.3 but minus that bit. Current in here, 7.3, fair enough. If I was to make this a little bit bigger, you probably don't need 7 milliamps to bias these diodes. We could probably make that 4K7 without breaking a sweat. And if we did, we would probably get slightly different answers. About 6 milliamps. We've effectively switched these transistors off a little bit by not having such a big voltage drop here. So now we've only got 1 milliamp in these diodes. 1 milliamp. A milliamp might be a bit paltry. Maybe if we go 2.2K. Try to pick values that exist. So in the E12 series, 6.6. That's 13.71. Below 15. Fair enough. I'd say that's probably about right, and we've got about 3 milliamps there. It's fine. Don't want to make this too small because all it really does is increase your power dissipation. If we were to look at the voltages in the circuit and want to hold them there, we can ask it for a right click button, by the way. Op data label. I can place it, right click it, get rid of that, and I can ask it for the current I in R3, and it'll tell me that 6.6 something or other. And I can make another one as well. maybe I want the voltage on this node, 13.71, and if I copy it I can get the voltage on this node, except that's really ugly, so let's not do that. What we can do is make a little wire there and pop it down like that. So you can subtract those two if you want, but you could just have another label. If you can't be bothered, you can do, now we need to know what nodes are involved. This is VN005, this is VN008, so James Bond is absent. VN005 minus VN008, 669 millivolts. That's believable. So that's the VBE, not 0.7, but 0.7 is just our rounding. You can ask it the same thing about any of these. If you ask the current in the capacitor, it will tell you there isn't one, because as far as a DC is concerned, it's perfect, there is no leakage. If you want the power in these devices, you can run your mouse over it, will tell you 42 milliwatts and 39 milliwatts or thereabouts, so about 40. If I wanted to know how good the source is at resisting changes in its output current, I could start sweeping this source. You don't have to do this, but we could. So we have a DC sweep, and that one's looks like it's V4, and we will sweep. We'll try for a decade, and we'll start at say 0 volts, and we'll stop. We've got to stop before we forward bias this junction. So we really ought to know what the voltage is on this base, but we know that it's going to be 15 less 1.4 less 6.2. So if we get the worst calculator in the universe up, 15 minus 1.4 minus 6.2, so we shan't go above 7 point something volts, so let's stop at 6, just to give it a bit of breathing space. Or we can't start at 0 because it's per decade. Start at 0.01. Number of points per decade, we'll have 100, that's loads. But this simulation won't take very long. If I put it down there, you may or may not have noticed that just before I drop that label down, dot op had a dot there instead of a semicolon. This means this one will not run, this one will now run. So DC sweep per decade, 100 points between 0.01 volts and 6 volts, and V4 is the swept voltage, everything else held constant. AC sources are switched off. So if I run this, if I run this, I will get a graph, and this is a V4, and I can plot what I like up here. So I'll Control Z, which is zoom in. Yep, I know, it really is. And you can see, sure enough, as I change V4, the current is changing. This is bad. What we really want is a straight line. But if you look at the vertical axis, you can see actually the current is not changing very much. I mean, we are what? 6.5850 to 5817. So our change is, we could subtract them, I guess, couldn't we? I'll try to do it in my head. 6.5817 minus 6.5850. So that's in milliamps. So it's I divide that by, times by 1,000. I'll get it in microamps. So 66 microamps is the change across the full range. So if you wanted to work out the output resistance of that source, you could try to do it from that, but there is a different way of working out the output resistance of the source, which is probably a bit better. You can see actually that if we hold around 2 volts, we'll end up with a reasonably straight region. It's actually, because this is logarithmic, it's changing far more here than it is in this bit here. This is almost no change, not much change in V4, and no change really in IC, not much change. So that's one way of trying to work out what your current source is up to. You could take the slope of the line as well if you wanted to do a V4 by DIC, and that would give you the output resistance in a little region. And that's actually what we'll do next. And I'll just close this, make that bigger, and I'll make AC voltage here. It doesn't matter about the value. so I'm going to divide it through by something else anyway. And we'll run AC sweep. So AC analysis per decade, 100 points, start from, I don't know, 0.01 up to 10 gig, don't want to miss anything. Now don't forget, your models are only good over certain frequency ranges. If you ask it to run at 100 terahertz, it will produce answers and they will be complete crap. It's up to you to interpret the data that it gives you. If you ask it silly questions, you'll get silly answers. So, AC sweep per decade, 100 points between 0.01 Hz and 10 gigahertz. Run. Frequency on the horizontal axis, whatever we like up here, and I can zoom in with Control Z, and I can ask it for the current. And in the region here, there's very little current flowing up into the source, effectively, or you can think of it as flowing out of the source if you prefer, but these are signal currents. There will be DC currents, and if you want to know them, I rest my mouse just there. Minus 6.58 milliamps is the DC condition, but on top of this, we have this AC as well. So the AC and the DC are there together in superposition, but this graph only showing us the AC, the small signals. So if I want the resistance looking into this collector, I'd say, well, R is V upon I. The V is the voltage on this node, which is fixed at 2 volts by this, 0 volts, sorry, because it's not 0 volts. 2 volts DC, 1 volt AC, which is 0 dB, which is where that 0 came from. R is V over I, so I can right click there and do divided by I, C, Q7. I'm reading that from just here. If I do that, I'll get something that measures in ohms. I don't really want to look at the current anymore, but if I just leave it for a second, the current that flows inwards is increasing. The voltage we saw just now is constant. No surprise, the resistance is dropping because the current is going up. Well, that makes sense, and if it wasn't that way, I'd be a bit worried. Let's just have a look at the resistance. So usually we have resistance in ohms, so I'll make it logarithmic, because otherwise you won't be able to see very well. But 2 megaohms, I should say, up to about a kilohertz. Now the audio range ends at 20 kilohertz, which is the highest anybody can hear. In fact, most people can't even hear about 15, which is somewhere around there, just to the right of the middle. So we're at probably 300,000 or 400,000 ohms by then. I put a line, I right click the name then. I can drag the line around and I can say, well, in this region, it's low frequency region, 2 megaohms by 20k, we're down to 257 kiloohms. And if you had some other design of current source that you're interested in, maybe you're comparing and want to see which is best, this would be the sort of metric that I'd be looking at. I'd draw them out in a SPICE file, I'd run them together and I'd plot the various curves and see which one I like the look of, and then I'd probably add up the cost of the components and consider the complexity, the amount of board space it would take up, maybe the power dissipation, how hot it's likely to get. All these things will be wrapped up together, and I will come to a decision as to which one I like. So that's that. In this particular case, I'll delete this now. This node here actually doesn't change voltage very much. This is your input voltage, and it's probably, if you're running an iPod into this, or Samsung phone, or record player, whatever you want, although you couldn't run a record player straight in, you'd have to have some preamplifier. The signal size is going to be about a volt, maybe 2 volts peak, roughly. You've got 0.7 here, and this resistor is pretty small, so it doesn't drop much of a voltage. The voltage swing on this node is going to be pretty tiny, so you don't really have to worry about a big dV by dt here. So is there an argument for using this current source? There is, because it's better than this current source. It will have higher output resistance than this one, but you don't really need to be terribly concerned because there isn't very much dV by dt here to start with. this person has chosen to put this source in, and we've got a very reasonable design for that current source, for the current that they wanted to design at. So I will leave it. Would I bother with this extra bit? Probably not. But it doesn't matter, it will do the job. Only thing we really haven't talked about at the moment is why you want 6 milliamps from here, or 6.5 or 7 or whatever it is. It is to some extent your choice, but you must allow enough current to flow in this half of the differential stage in here to charge up this capacitor in the time that will allow the signal swing on this node that you want, because your dV by dt across here involves you charging this capacitor and discharging it. If you want to have full power out of your amplifier, you have to have very large amplitude sine waves at quite high frequencies, which means you've got big dV by dt's. You've got to charge and discharge this capacitor fast enough, otherwise you'll get slew rate distortion, which we discuss in 225. So you don't want this current to be too small. Now we could, if we wanted to, sit down and work out how long you'll have to charge up this capacitor and what is the minimum size and all the rest of it. But this video is already getting pretty long, and we might do that when we actually talk about this stage. So as far as the current source is concerned, we are more or less finished.